We will now look at equivalence relations. So if we're given a partition of a set A, the relation induced by the partition is defined on A as follows. For every xy in A, x is related to y if and only if there is a subset, A sub I, of the partition such that both x and y are in A sub I. So we have the set A, which is the set 0, 1, 2, 3, 4. And we're going to consider the following partition of A. The set of the set 0, 3, 4, the set of 1, and the set of 2. We wish to find the relation that is induced by this partition. So what we'll do is we'll first consider the subset 0, 3, 4. So remember, the relation induced by a partition is such that for every xy in A, there x is related to y if and only if there is a subset A sub I of the partition such that both x and y are in it. So from this subset, we find that 0 is related to 0, 0 is related to 3, 0 is related to 4, 3 is related to 0, 3 is related to 3, 3 is related to 4, 4 is related to 0, 4 is related to 3, and 4 is related to 4. So that is just from that first subset. If we now look at the subset of 1, we find that 1 is related to 1. And if we just look at the subset of 2, we find that 2 is related to 2. So R, the relation itself, remember relations are sets of ordered pairs. So 0, 0, 0, 3, 0, 4, 3, 0, 3, 3, 3, 4, 4, 0, 4, 3, 4, 4, 1, 1, and finally 2, 2. So that is the relation that is induced by this given partition. So if we let A be a set with a partition and let R be the relation induced by the partition, then this relation is reflexive, symmetric, and transitive. So given any set, any relation that is induced by a partition of that set will automatically be reflexive, symmetric, and transitive. So let's go ahead and prove it. So suppose that A is an arbitrary set. For simplicity, we will assume that the partition consists of only a finite number of sets. The proof in which the partition has an infinite number of subsets is identical. So we denote the partition of A by script P is equal to the set A1, A2 through AN, right? So each of these A's is a partition. Well then, A sub I intersected with A sub j would have to be empty whenever I is not equal to j, and also the union of all of these AIs would be equal to A. This is by definition of the partition of a set. Now, consider the relation R on A, defined as follows. For all x, y in A, x is related to y if and only if there exists some AI in script P such that X is in AI and Y is in AI. Right? So this is the relation induced by the partition. We will now divide the proof into 3 sections, or 3 sub-proofs, one for each of the 3 properties. So first, let's do the proof of reflexivity. So suppose that X is in A. Since script P is a partition of A, it follows that X would be in AI for some I, right? So there has to be some subset in the partition of A such that X is in it. This is by definition of a partition. Well, that means that there exists an AI in script P such that X is in AI and X is in AI, right? So this means that X is related to X. So this here actually should have been X is in A sub I. Since X is related to X, this means that it is reflexive, and so the proof of reflexivity is complete. We will now look at the proof of symmetry. So suppose that xy is in A such that X is related to Y. Then this would mean that there exists some AI in script P such that X is in AI and Y is in AI. By the commutative property of conjunction, the statement there exists an AI in script P such that Y is an AI and X is an AI is also true. Right? All we did was flip the order of the conjunction. And if you remember back at logic, you're allowed to do that. They're equivalent. So Y is related to X by definition of R. Well, this means that it is symmetric. And so the proof is complete. So let's now look at the proof of transitivity. Suppose that X, Y, and Z are in A such that X is related to Y and Y is related to Z. Then there must exist some AI in script P such that X is an AI and Y is an AI, and there must also exist some A sub J in script P such that Y is in A sub J and Z is in A sub J. What we will now show is that A sub I is equal to A sub J. If we can show that, then that means that X and Z would be in the same partition, and so X is related to Z. So we're going to do this by contradiction. Suppose that A sub I is not equal to A sub J. Then this would mean that A sub I intersected with A sub J is the empty set, since both A sub I and A sub J are in script P, a partition of A. Notice that Y is in A sub I and Y is in A sub J. Thus, A sub I intersected with A sub J contains at least one element, namely the element Y. But this would mean then that the intersection of A sub I and A sub J is not empty. This contradicts the fact that it must be empty. So, A sub I must equal A sub J. This means then that X, Y, and Z are all in A sub I. So there does exist an A sub I in script P such that X is in A sub I and Z is in A sub I. Thus, X is related to Z, so R is transitive, and the proof of transitivity is complete, and overall, our proof of the theorem is now complete. So we now define an equivalence relation. Let A be a set and R be a relation on A. R is an equivalence relation if and only if R is reflexive, symmetric, and transitive. So equivalence relations are just simply relations that are all reflexive, symmetric, and transitive. So if we let X be the set of all non-empty subsets of the set 1, 2, 3, and we define a relation R on X as follows. For all A, B, and X, A is related to B if and only if the least element in A equals the least element in B. We want to prove that R is an equivalence relation on X. So that is, we have to show that R is reflexive, symmetric, and transitive. So first, the notation. So let min of A denote the least element in A. So this is just simply for simplicity in the writing of the proof. So first, the proof of reflexivity. So let A be an element of X. Now this is trivial, right? Because obviously the least element in A is equal to the least element in A, which means that A is related to A, and so R is reflexive, so that completes the proof of reflexivity. We must now prove that R is symmetric. So proof of symmetry. So we let A and B be elements of X, such that A is related to B. So this means that the least element in A is equal to the least element in B. But equality equals is commutative. So this would mean that the least element of B is equal to the least element of A. So B is related to A, and that concludes the proof of symmetry. So all that's left is the proof of transitivity. So let A, B, and C be elements of X such that A is related to B and B is related to C. Then this would mean that the least element of A is equal to the least element of B, and the least element of B is equal to the least element of C. Well, if the least element of A is the least element of B, and the least element of B is the least element of C, then the least element of A must be equal to the least element of C. Thus, A is related to C, and that proves transitivity, so that completes our overall proof. Right? That's all we had to do. We just had to show that this relation is reflexive, symmetric, and transitive. So let's now suppose that there's an equivalence relation on a certain set. If A is any particular element of the set, then we can ask, what is the subset of all elements that are related to A? Right, so this is our next definition. Suppose A is a set and R is an equivalence relation on A. For each element A in A, the equivalence class of A, which is denoted as A in square brackets, and is called the class of A, is the set of all x in A such that x is related to A. So the equivalence class of an element is the set of all elements that are related to it. So notice that this set is guaranteed to have at least one element, namely A itself, right? Because we're dealing with an equivalence relation, that means it's reflexive, so every element would be related to itself. So define a set A as the set 0, 1, 2, 3, 4, and define a relation on A as follows, so it's given here. We wish to determine whether this is an equivalence relation on A, and if it is, to find the distinct classes of R. So when dealing with a finite relation, remember the easiest way to show reflexivity, symmetry, and transitivity is a directed graph. So let's have 0 there. Let's have 1 there. Let's put 2 here. Let's put 4 there. And let's put 3 there. Right, so we have 0, 0. Then we have 0, 4. We have 1, 1. We have 1, 3. We have 2, 2. We have 3, 1. 3, 3. 4, 0. And 4, 4. So from this directed graph, we can conclude that R is an equivalence relation. And so that completes the proof that R is an equivalence relation. All we have to do now is find the distinct classes of R. So start with the element 0. So remember the classes, or in this case the class of 0, is the set of all elements that are related to 0. So that would be, from the directed graph, 0 and 4. So look at 1. That would be 1 and 3. 2 would be just 2. Then we have 3. Well, 3 would be 3 and 1, but notice that's the same as the class of 1. And if we look at 4, it'd be 4 and 0, which is the same as the class of 0. So these are the only 3 distinct classes. Now let X be the set of all non-empty subsets of the set 1, 2, 3, and define a relation R on X as follows. For all A, B in X, A is related to B if and only if the least element in A equals the least element of B. And we want to find the distinct classes of R. Well, we already have shown that this is an equivalence relation. So let's look at the class of the set 1. So this would be the set 1, 1, 2, set 1, 3, and the set 1, 2, 3. If we now look at the class of the set 2, this would be the set 2 and the set 2, 3. We now look at the class of the set 3. This would just be the set of the set 3. And now notice that we have now accounted for every possible subset of X. So these would be the only 3 distinct classes. So now we define a relation on the real numbers as follows. For all X and Y that are real numbers, X is related to Y if and only if X is equal to Y. Describe the classes of R. Well, if we let A be a real number, then the set A, or the class A rather, right, is the set of all real numbers X such that X is related to A. But by definition of the relation, this would be the set of all real numbers X such that X is equal to A. Well, there's only one real number to equal A, and that would be A itself. So that's just the set A. So for all real numbers A, the class of A is just the set of A itself. And there's going to be an infinite number of these. So now suppose A is a set, R is an equivalence relation on A, and A and B are elements of A. If A is related to B, then the class of A is equal to the class of B. So let A be a set, let R be an equivalence relation on A. Suppose that A and B are elements of A such that A is related to B. Right? So remember, what we have to show is that the class of A is equal to the class of B. Well, classes are sets. And the way to prove that 2 sets are equal is to show that they are subsets of each other. So first, let's suppose that X is an element of the class of A. Then by definition, this means that X must be related to A. However, we also know that A is related to B. And so what we have is X is related to A, and A is related to B. This means that X is related to B, right? This is because R is an equivalence relation, meaning that R is transitive. So this means that X is in the class of B, and so remember that this shows that the class of A is a subset of the class of B. Now suppose that X is an element of the class of B. Then this means that X must be related to B. However, again, we know that A is related to B, and so we also know that B is related to A. Once again, because R is an equivalence relation, meaning R is symmetric. So now we have X is related to B, and B is related to A, so we can conclude that X must be related to A. Again, because R is an equivalence relation. So this means that X is in the class of A, which means that the class of B is a subset of the class of A. So the class of A must be equal to the class of B, and the proof is thus complete. Now, if A is a set, R is an equivalence relation on A, and A and B are elements of A, then either the class of A intersected with the class of B is the empty set, or the class of A is equal to the class of B. So the key in this proof is the or. So if we assume that one of these two statements is not true, and show that the other statement must be true, then we've proven the disjunction, right? The disjunction is false only if both are false. So to be true, we only need one of them to be true. So we suppose that A is a set, R is an equivalence relation on A, B are elements of A, and we'll assume that the class of A intersected with the class of B is not empty. Right, so we're going to assume the negation of this statement. Then that means that this statement, the second statement here, must be true. That's what we have to show. So since the class of A intersects the class of B is not empty, there has to be an X in the intersection of class of A and class of B. So this would mean that X is in the class of A and in the class of B. So X is related to A and X is related to B. However, since R is an equivalence relation, right, it is symmetric and transitive, so we have A related to X means A is related to X and X is related to B, which implies that A is related to B. I think this here should have been a B. Can I actually just make it look like a B? I can't. Alright, so since B is related to X would be related to B. So we have A related to X and X related to B. No, I'm sorry. I had that right the first time. I apologize. This actually here should have been X is related to A, which implies A is related to X. My apologies. So, since A is related to B, we can conclude from the previous lemma, right, the one we just proved, that the class of A must be equal to the class of B. Since that is what we wanted to show, the proof is complete. Right, now here is what we are working up to. If A is a set and R is an equivalence relation on A, then the distinct equivalence classes of R form a partition of A. So suppose that A is a set, R is an equivalence relation on A. Again, for simplicity, we shall assume that R has only a finite number of distinct equivalence classes, which shall be denoted as the class of A sub 1, class of A sub 2, so on and so forth, class of A sub n. The proof where there are an infinite number of equivalence classes is identical. But what we need to show is that this collection of classes forms a partition. So remember, to be a partition, their unions must give you a set, and they must be mutually disjoint. So we will first prove that A is the union of each of all of these equivalence classes. So suppose that X is an A. Well, then X has to be related to itself because R is reflexive. This means that X is in the equivalence class of X, which would mean that it must be in the equivalence class of A sub I, of some A sub I, right? Because these are the only distinct equivalence classes. Since X is related to itself, it must be in one of them. Well, then, that would mean that it's in the union of all these A sub I's. So A would be a subset of that union. Now suppose that X is in the union. Then this means that X is in the class of A sub I for some I. However, each of these classes is a class of the equivalence relation R. And we know that R is a subset of A cross A. So that would mean that the classes are subsets of A. Hence, the class of A sub I is a subset of A for each I. Thus, X is in A, which would mean that the union of these classes is a subset of A, and hence A must be equal to the union of the classes. So that completes the proof of that. Now all we have to do is show that these classes are mutually disjoint. So that you have to show that the intersection of the class of A sub I with the class of A sub j is empty whenever I is not equal to j. Well, this is simple. Since the classes are distinct, the class of A sub I is not equal to the class of A sub j whenever I is not equal to j. So this means that their intersection must be empty by the previous lemma, right? The lemma that we just proved. And so that proof is complete. That is all we had to show, and hence these distinct classes form a partition of the set. So we now define a relation T on the set of integers as follows. For all n in integers, m is related to n if and only if 3 divides m minus n. We are going to describe distinct equivalence classes of R. I'm sorry, of T. Now it's already been shown that T is an equivalence relation, right? So we let A be an integer. Then the class of A is equal to the set of all integers x such that x is related to A, and by definition of T, this is the set of all integers x such that 3 divides x minus A. Another way to write this then is the set of all integers x such that x minus A is equal to 3q for some integer q. Right, that is by definition of divides. And so we can write this as the set of all integers x such that x is equal to 3q plus a for some integer q. Right? However, this fits the form of the quotient remainder theorem. So by the quotient remainder theorem, we must have zeros less than or equal to a less than 3. Which means a is either 0, 1, or 2. And so the distinct classes, we have the class of 0, which is the set of all integers x such that x is equal to 3q plus 0. We have the class of 1, which is the set of all integers x such that x is 3q plus 1. And we have the class of 2, which is the set of all integers x such that x is equal to 3q plus 2. And these are the only distinct classes of T. Right now, as we've been seeing in the past several examples, there are several ways to represent an equivalence class. So in the previous example, right, so here, we used the class of 0 to represent the multiples of 3. So we really could have just as easily written this class here as the class of 3, or the class of 6, or the class of -3, right, or et cetera, et cetera, et cetera. So we could have used any multiple of 3. So this leads to our next definition. If we suppose that R is an equivalence class of A, and S is an equivalence class of R, a representative of the class S is any element A such that the class of A is equal to S, and this should not have been class, this should have been equivalence relation. Right, so there's multiple ways of representing equivalence classes. As we will study very shortly, when we're dealing with modular arithmetic, we will use the smallest possible number. So we'll use 0, 1, and 2 to represent the classes of congruence modulo 3. And that will conclude our study of equivalence classes. In the next video, we will actually now look at modular arithmetic, which is actually a pretty cool branch of number theory.